Hello and welcome back to tonight's storytelling journey. Throughout the long history of hundreds of millions of years, life on Earth has never followed a smooth and easy path. Many times it has been pushed to the very edge. The seas once changed. The sky once darkened. Volcanoes once left their mark upon the atmosphere. Kingdoms of living beings that once flourished quietly gave way to more silent survivors. And yet the strangest thing of all is this life continued. Before we begin, gently, let me know where in the world are you listening from. Outside your window right now, is it late at night, early dawn, or a quiet afternoon? And where you are sitting, what time does the clock show? Let that answer drift slowly through your mind, because tonight we will journey back into spans of time so distant they are almost impossible to imagine. An Earth without humans, without the sound of traffic, without rooftops, without maps, without names. Only ancient oceans, drifting continents, the first forests, strange creatures crawling across the sea floor, and a planet still learning how to become the world we know today. Tonight we will travel through the 5 greatest mass extinctions in Earth's history, not only to see what was lost, but also to understand how life found its way back little by little through the deep darkness of time. Before we step into the 5 greatest mass extinctions in the history of Earth, let us begin very slowly, not with the roar of volcanoes, not with an asteroid blazing across the sky, and not with the image of ancient creatures vanishing in one violent instant. Let us begin somewhere much quieter. A cliff face resting silently in the evening light. A thin layer of sediment pressed tight by time across millions of years. A small fossil no larger than the tip of a finger lying still inside the stone like a memory that has fallen asleep. Imagine you are standing before an ancient cliff where layers of rock are stacked upon one another like the enormous pages of a book. The lower layers are older, the upper layers are younger. Every streak of color, every crack, every grain of fossilized sand was once part of an older world. One layer may once have been a sea floor. Another may have been the mud of a shallow body of water. Another may have held the shells of clams, corals, mollusks, plankton, or the faint crawling traces of creatures that passed through that place long before human beings appeared. If Earth had a diary, that diary would not be written in ink, it would be written in stone. And the readers of that diary are geologists and paleontologists, people who have learned to listen to the past with patient eyes. They cannot travel back 400 million years to witness the ancient oceans for themselves. They cannot hear the waves of the Ordovician seas, cannot see the Devonian reefs, cannot walk across the distant lands of the Permian. But they can kneel before a layer of rock, open it, and recognize that a world is still preserved within it. A flattened shell, a strange mineral trace, a boundary between 2 layers of stone where the lower layer is still dense with fossils while the layer above suddenly becomes poorer, emptier, and strikingly different. It is these changes that led scientists to begin asking a question: what happened here? Not every disappearance in the fossil record is a mass extinction. The fossil record is not perfect. There are soft-bodied creatures that leave almost no trace. There are places where life once existed, but where the conditions were not right for fossils to form. There are layers of rock that have been eroded, crushed, altered by heat and pressure, or buried deep beneath the ground. So reading the history of life is never like reading a book preserved perfectly from the first page to the last. It is more like gathering fragments of an ancient letter, some parts clear, some parts scorched, some parts missing, and then trying to understand the larger story hidden between the gaps. But precisely because that record is imperfect, when a sign appears again and again in many places across the world, it becomes far more remarkable. If in one cliff face a group of organisms disappears, we might think it was a local event. Perhaps the environment in that place changed. Perhaps the ocean current shifted. Perhaps the rock layer did not record the story completely. But if at the same moment in geological time, across different continents and different marine regions, many groups of organisms all decline sharply, then the story is no longer about a small coastline. At that point, perhaps the whole planet had changed. That is how the idea of mass extinction gradually emerged. A mass extinction is not simply the disappearance of many species. Throughout Earth's history, extinction is always happening. One species appears, another disappears. That is a natural part of evolution, like leaves falling to make room for the next season. But a mass extinction is different. It is a time when the rhythm of disappearance suddenly rises on a vast scale. Ecosystems that once seemed stable are shaken. Groups of organisms that had existed for tens of millions of years suddenly can no longer hold their place. The seas, the land, the climate, the atmosphere, all of them may change together in ways that many species cannot adapt to quickly enough. What is remarkable is that scientists often see these great changes most clearly through marine life. Not because life on land is unimportant, but because the sea preserved memory better during many ancient periods. Shells, corals, trilobites, brachiopods, mollusks, and tiny creatures living in the water column and on the seafloor all left their marks in sediment. When they appear abundantly, the rock becomes rich with memory. When they suddenly vanish, the rock becomes a silence. Picture an ancient seafloor. Sunlight passes through the shallow water. Below, countless small creatures live, crawl, filter food, cling to stone, and hide in the mud. Over time, their remains fall, are buried, and become part of the sediment. Fine layers of mud settle one upon another. One season passes, then 1,000 years, then 1,000,000 years. Eventually, that seafloor becomes stone. Those tiny creatures are no longer creatures. They have become the handwriting of Earth. Then on a day far in the future, when that stone has been lifted into mountains, when the sea has retreated, when wind and rain have worn the surface down, human beings find them. A modern hand touches a shell that has lain still for hundreds of millions of years. The moment is quiet, but within that quiet, there is something almost overwhelming, 2 ages of time touching one another. To understand mass extinctions, scientists do not look only at a single fossil. They look at entire communities of life. They ask, before this boundary, which species were present? After this boundary, which species remained? Which groups disappeared completely? Which groups declined and then recovered? Which groups seemed to be less affected? And what in the rocks shows that the environment had changed? Sometimes the answer lies in chemical composition. The ratios of carbon-oxygen and sulfur isotopes in the rocks can suggest changes in climate, the carbon cycle, sea temperature, or oxygen levels in the water. Sometimes the answer lies in the color of the rock. Black rocks rich in organic matter can be a sign of oxygen-poor seas where dead organisms sank down but did not fully decompose, as they would in an oxygen-rich environment. Sometimes the answer lies in volcanic ash in tiny minerals or in a thin clay layer that appears in many places. From the outside, a layer of rock may look like nothing more than a dark line across a cliff. But to someone who knows how to read it, it can say that the atmosphere changed, that the ocean became more suffocating, that temperatures rose or fell, that sea level rose or retreated, and that the creatures that once lived in that world had to face an environment no longer familiar to them. Geological time is also something we must feel very slowly. To us, 1,000 years is already distant. 10,000 years is almost beyond ordinary memory. But in the story of Earth, numbers like these are only a breath. When we say a biological crisis took place over a few 100,000 years, it may sound very long compared with a human life. But for a planet more than 4 billion years old, it can be a very rapid change. This is what makes mass extinctions both difficult to imagine and quietly terrifying. They do not necessarily unfold like a single scene where everything changes in one morning. Some events may include a violent moment, but others stretch across thousands, tens of thousands, even hundreds of thousands of years. For each individual creature, life may still seem like ordinary existence, searching for food, avoiding predators, reproducing, moving with the seasons. But from the perspective of stone, the whole world is slowly sliding into another state. An ocean may lose oxygen little by little. A climate may warm or cool across many generations. A shallow sea may gradually shrink as sea level falls. An ecosystem may not collapse all at once, but thin out, weaken, and slowly lose its smaller links. By the time scientists look back through fossils, they see a boundary. But behind that boundary were countless mornings, countless seasons, and countless living beings existing in a world that was becoming harder and harder to recognize. And then when that boundary is compared across the planet, the larger picture begins to appear. Scientists realize that over roughly the last 500 million years, the history of complex life has passed through 5 especially great mass extinctions. They were not all the same. Each had its own setting, its own rhythm, its own possible causes, and its own groups of organisms that were affected. One was linked to cold climate change and sea level. Another was connected to prolonged oxygen loss in the oceans. Another was tied to enormous volcanic activity. Another changed the balance of ecological power on land. And one became famous because an asteroid left a gigantic scar on the planet. But in this chapter, we do not yet need to step deeply into each of those events. What matters more is understanding how science recognized them. Not through legend, not through imagination, but through traces, measurements, comparisons, debate, verification, and patience. The science of mass extinction was not discovered fully formed in a single day. It was built from many pieces: a fossil in Europe, a rock layer in North America, a sediment sample from the sea floor, a chemical analysis in a laboratory, a date determined more precisely through volcanic minerals, an old hypothesis revised, an estimated number adjusted when new evidence appeared. So, when we speak of mass extinctions, we also need to keep a certain humility. Some things are very well established. Major biological declines did happen. They left widespread traces in the fossil record, and they changed the direction of life. But some questions are still being studied. Exactly how quickly each process unfolded, which causes were primary, which were secondary, why one group survived while another disappeared, and why an ecosystem could endure up to one point before it could no longer continue. That incomplete certainty does not make the story less compelling. On the contrary, it makes the story closer to the true nature of the past. The past does not lie before us like a finished film. It is buried in stone, hidden by time, fragmented across layers of sediment scattered around the world. Each new discovery is like a small lamp being lit in a very large, very dark room. And when many lamps are lit together, we begin to see the outlines of lost worlds. In one place, fossils show that the sea was once full of hard-shelled creatures. In another place, at roughly the same time, diversity also declined. Farther away, a rock layer of the same age tells a similar story. The scattered pieces begin to fit together. Earth was not simply experiencing change in one local sea. Perhaps the entire planetary system had shifted. At that moment, a name was given not to make the story more dramatic, but to describe its true-scale mass extinction. But if the story stopped at disappearance, it would not be the whole story. Because in the rock layers after the crisis, scientists do not find only emptiness. They also find signs of return. At first, life is sparse. Then it becomes more diverse. Surviving groups begin to spread. New forms appear. Different ecosystems gradually take shape. There were organisms that had not been especially prominent in the old world, but after the disruption they moved into the spaces left behind by other groups. There were quiet, small, evolutionary branches that had seemed unimportant, yet became the foundation for later ages. This is one of the deepest patterns in the history of life. After each time Earth changes, life does not return exactly as it was. It rearranges itself. It experiments. It opens new paths. So the fossil record is not only a cemetery of lost species, it is also a chronicle of adaptation. In stone, we see endings, but we also see beginnings. We see kingdoms of life that once flourished and then left the stage. But we also see quiet survivors, not loud, not powerful in any obvious way, still clinging to a narrow passage in time and moving forward. Perhaps that is why the story of the 5 mass extinctions not only overwhelms us, but also makes us reflect. Earth is not an unchanging place. It has been colder, hotter, darker, more suffocating, and far stranger than the world we live in today. The things that now seem steady, forests, oceans, grasslands, birds in the sky, small mammals, insects, all of them are the result of a history that is very long, very fragile, and very wondrous. When we place a hand upon a fossil-bearing stone, we are not only touching a creature that once lived, we are touching evidence that life was here long before us. It passed through shallow seas that vanished continents, that broke apart atmospheres that changed, and ages when the map of the world looked nothing like it does today. And along that journey, it faced many narrow doors, so narrow that only a very small part could pass through. Our first chapter, therefore, is a chapter about learning how to see a layer of rock as more than rock, to see a fossil shell as more than a shell, to see an absence in the record of life as more than emptiness, but perhaps as the sign of a global event. When we learn to see in that way, Earth begins to tell its story, slowly, deeply, but clearly. And from those silent pages of stone, we prepare to step into the first great upheaval. It was a world where complex life on land had barely begun. A world in which the sea was the main stage, where ancient creatures lived in shallow waters beneath the dim blue light of an ancient sun. Then the climate began to change. Ice formed. Sea levels fell. The once life-filled shallow seas began to shrink. But before we move on, hold on to the image of this chapter, a silent cliff face in the wind, a fossil layer lying between 2 ages, and a very small question that opens the deep history of an entire planet. What happened to life on Earth? From that question, the true journey begins. The Ordovician period, roughly 440 million years ago. If you could stand upon Earth at that time, you would see a planet very different from the one we know today. The continents did not lie in the familiar positions we see on modern maps. Most complex life still remained in the sea. The land was almost empty of large living creatures. There were no dense forests covering the continents in green, no insects chirping in the grass, no animal footprints pressed into the mud. Wind may have swept across bare stone surfaces, across silent barren lands, while the most living part of the planet lay beneath shallow waters of deep blue. And it was there in those ancient seas that life once flourished. Imagine yourself drifting very slowly beneath the Ordovician water. Sunlight falls down through the clear, gentle, blue-green sea. On the seafloor, there is no white sand like the beaches of the modern world, but a realm filled with strange and unfamiliar forms. Trilobites crawl slowly across the muddy bottom. Brachiopods open their two shells to filter food from the water. Ancient corals and sponges build living structures. Flower-like sea creatures anchor themselves to the sea floor, stretching their soft arms into the current. Farther away in the water column, tiny organisms drift with the sea, becoming part of a complex web of life no human eye had ever witnessed. To us, those creatures may seem alien, even difficult to name. But to Earth, at that time, they were the inhabitants of a thriving world. The Ordovician Ocean was not an empty body of water. It was a vast stage where life experimented with shape, with feeding, with clinging, with crawling, with floating, with protecting itself. During that time, marine biodiversity rose sharply. Many groups of sea creatures spread across shallow waters. Reef-like communities developed. Seafloor ecosystems became more crowded. It seemed as though life had found a stable rhythm within the heart of the ocean. But there was one thing no creature in that world knew. That stability would not last forever. Somewhere within the immense workings of the planet, the climate began to change. Not through a sign that could be easily recognized in a single morning. No warning bell rang across the ocean. No clear boundary appeared for those small creatures to understand that their world was entering a dangerous age. The change came more slowly, more deeply, and more coldly. Earth began to enter a major ice age. Part of the supercontinent Gondwana lay near the South Polar region at that time. As the climate cooled, ice began to accumulate on land. Each season grew colder. Each layer of snow failed to melt completely. Each mass of ice thickened with time. And as water became locked away inside enormous ice sheets on the continent, sea levels began to fall. This may sound simple, but for Ordovician life, it was a devastating change. Because most complex organisms at that time lived in shallow seas. Shallow waters along continental margins were places where sunlight could reach the bottom, where nutrients circulated, where countless creatures could cling, crawl, filter food, and reproduce. They were the great cities of ancient life. When sea level fell, those shallow seas began to shrink. Places that had once been seafloor were gradually exposed to the air. Communities of organisms that had lived stably in warm, shallow water suddenly lost their living space. Picture a wide, quiet sea once filled with countless small movements. Then the water slowly retreats, not in a single day, but over a long span of time, long enough for generations of organisms to be born into a world that keeps growing narrower. Vast continental shelves are drained. Seafloor regions that once had light and food become dry mud, bare stone, or colder waters, far more difficult to live in. For creatures that cannot swim far, cannot leave the bottom, cannot adapt quickly. That change is like having their home slowly pulled away, piece by piece. This was the first blow of the Ordovician mass extinction. It did not come with fire, it came with ice. And that is what gives this crisis its own particular coldness. When we think of mass extinctions, we often imagine violent scenes, darkened skies, erupting volcanoes, falling asteroids, seas thrown into chaos. But the first great mass extinction on Earth began with the slow contraction of the ocean, with the spreading cold, with coastal habitats being withdrawn from the biological map of the planet. In the sea, the organisms could not see the ice sheets of Gondwana. They did not know that the water of the world was being locked away in ice on a distant continent. They only felt the environment around them changing. The temperature was different, the depth was different, the currents were different. Places to cling sources of food light. Everything was no longer as it had been. A trilobite may still have crawled across the seafloor as it always had. A brachiopod may still have opened its shell to filter the water. A cluster of ancient corals may still have clung to the rocky bottom. But the world around them was shrinking. Shallow seas that had once been widely connected were now being divided. Populations of organisms became isolated. Species that were used to living within a narrow range of conditions began to struggle. Meanwhile, species with broader distributions, greater tolerance for change, or better chances of enduring unstable conditions may have had a higher chance of surviving. This is a quiet rule in many biological crises. Sometimes survival does not belong to the strongest species in the way we often imagine. Not the largest species, not the one with the most beautiful shell, not the one that had once been most abundant. Survival may belong to creatures with wider ranges, fewer strict requirements, greater tolerance for change, or simply to those that happened to be in the right place when the upheaval came. But the Ordovician did not have only one pulse of change. After the cold and glacial phase, Earth shifted into another state. As the climate warmed, the ice began to melt. Water returned to the oceans. Sea levels rose. At first, this may sound like a rescue. Shallow seas could return. Living space could expand. But for many ecosystems that had already been weakened, a rapid change in the opposite direction could become a second blow. The ocean is not merely a vast container of water. It is a living system with layers of water, currents, temperature, oxygen, nutrients, and light. When the climate changes strongly, ocean circulation can also change. Oxygen-poor waters may spread. Marine environments can become unstable. For organisms that had just endured the loss of habitat caused by falling sea levels, having to face rising seas changes in seawater chemistry and low oxygen conditions in many areas was too great a challenge. Imagine yourself at the bottom of a sea that has just been covered by water again. The surface above is calm. Light can still filter down. But near the bottom, the water feels heavier and more suffocating. There is less oxygen. Creatures that once filtered food from the current no longer receive the familiar conditions they depended on. Species fixed in place cannot leave. They cling where they are in a world changing color in a way that is very slow, very difficult to notice, but strong enough to weaken an entire community. In many places, life did not disappear in a single instant. It gradually thinned out. One group no longer appeared in the rock layer above. Then another group became less common. Forms that had once been widespread suddenly became rare. Communities that had once been rich became simpler. Fossils began to tell the story of an absence. When scientists look at the Ordovician-Silurian boundary, they do not see merely a local story. They see the traces of a global event. Many groups of marine organisms declined sharply. A very large proportion of species disappeared from the fossil record. For the history of life, this was the first major mass extinction among the 5 most famous mass extinctions. But to truly feel this story, we should not look only at numbers. Numbers help us understand scale, but they cannot create the image by themselves. Behind every percentage were living communities that once existed, sea floors once full of movement, species that had adapted to an old world, then could not keep pace when that world changed too deeply. A planet where life had only recently expanded powerfully through the oceans was forced to face its first great test. What makes the Ordovician extinction especially distinct is that it happened in a world where life on land had not yet become central. For that reason, the ocean was almost the whole story. If the sea changed complex, life changed. If the shallow waters collapsed, most of Earth's biological stage trembled with them. In the modern world, we are used to thinking of land as the main realm of life. Forests, grasslands, cities, animals, human beings. But in the Ordovician, try to forget all of that. Forget birdsong, forget leaves, forget the shadow of forests. Let there be only the sea stretching across continental shelves, warm, shallow seas, deep blue waters beneath an ancient sun. Seas holding creatures whose forms seemed to come from a distant dream. And then that sea began to retreat. That is the central image of this chapter. The ocean, the greatest home of life, beginning to pull back from its richest biological regions. It did not vanish completely. But the most important places, the shallow waters where life had grown densely, were reduced. A city may still remain on the map, but its roads are cut off, its markets abandoned, its water supply altered, its climate grown harsh. In the end, that city is no longer itself. On the Ordovician seafloor, fixed organisms suffered heavily. Species that needed a certain depth, a certain bottom type, a certain current, could not easily move with the changing sea. Groups such as brachiopods, trilobites, ancient corals, graptolites, and many other marine creatures were affected in different degrees. Some lineages disappeared, some declined, and later left surviving branches. Some groups endured and continued into the period that followed. Here the story should not be told as a clean cut between presence and absence. The history of life is more complicated than that. A mass extinction does not always erase an entire group. Some groups lose many species, but do not vanish completely. Some seem weakened, but later recover in the world that follows. Some are damaged in one place, but survive somewhere else. It is precisely this complexity that makes the fossil story feel true. And within that truth, we see something very important. Life is not a single block. It is countless different strategies. Some species cling in place. Some crawl, some drift. Some filter food. Some hunt. Some require shallow waters. Some can survive across a wider range of conditions. When the planet changes, those strategies are tested. Some become fragile. Others by chance become better suited to the new world. That is why after the Ordovician mass extinction, life still did not end. Despite the enormous losses, the ocean did not become an eternal emptiness. Surviving organisms continued to exist. Marine ecosystems were gradually rebuilt. In the time that followed, life continued onward, not by returning to exactly the same form, but by rearranging itself. The empty spaces left behind by lost species became room for the remaining branches to expand. The world after the Ordovician was not entirely the same as the world before it. Perhaps that is one of the deepest truths we see when looking at mass extinctions. They do not only end a chapter, they also rewrite the opening of the next one. But at this point in the journey, let us not hurry too far ahead. Let us remain for a little longer with the Ordovician Sea after the crisis. Imagine the water has returned in some regions. Waves still move, light still falls upon the sea surface. But the community of life below has changed. Familiar species are no longer as abundant as before. Some forms have disappeared from the landscape. The survivors appear more sparsely, then slowly begin to spread. In that quietness, Earth is no longer the Earth it once was. There was no one there to mourn a world that had passed. No observer recorded the names of each vanished species. No memory, no song, no monument. Only sediment continued falling to the sea floor. Only mud covered old shells. Only time slowly pressed those traces into stone. And hundreds of millions of years later, when a scientist split open a slab of rock, the story could finally begin to be heard. One layer full of fossils, one poorer layer above it, a thin boundary between two worlds. From that boundary, we understand that life once stepped through a very narrow door. Many species did not continue, but some did. And because of those that remained, the history of Earth did not stop in the Ordovician. It moved onward into new seas, new continental shores, and new evolutionary experiments. The Ordovician mass extinction teaches us that a planet can change through cooling, through falling sea levels, through upheavals that do not need an explosion, and yet are powerful enough to shake all of life. It also teaches us that even the places that seem most peaceful, like a sunlit shallow sea, still depend on balances far greater than themselves: climate ice, sea level oxygen currents, and the positions of continents. Life does not exist separately from Earth. It is held up by Earth. And when Earth changes its rhythm, life must change with it or be left behind in layers of stone. And so the first great crisis has passed. The Ordovician Ocean once collapsed, but it did not fall silent forever. From the waters that had shrunk from the communities that had been diminished from the surviving branches of life, existence began once again to find a path. Not loudly, not triumphantly, in any glorious way. Simply continuing in cold water and new sediment, in the spaces that time had left behind. And as we leave the Ordovician, carry that image with you. An ancient ocean retreating beneath a cold sky. Tiny creatures clinging to the seafloor, and life, though pushed into its first great trial, still refusing to disappear from the story of the planet. But ahead of us, Earth would change again in an even stranger way. Next time, it would not only be ice and retreating seas that altered the world. Something that seemed like a sign of growth, the first forests on land, would begin to affect the oceans in deep and unexpected ways. And from there, life would enter a new chapter, slower, more complex, and filled with surprising connections between land, water, trees, and the sea. After the Ordovician mass extinction, Earth did not fall into silence. The ocean had once contracted beneath the deep cold of an ice age. Many creatures had vanished from the layers of stone. But life continued. It did not return exactly as it had been. It did not rebuild the old lost world in the same form. It moved forward in its own way, slowly and patiently, like a small stream finding its path through cracks in the rock after a long winter. And then tens of millions of years passed. We enter the Devonian period. If the Ordovician was the story of an ancient ocean that almost held the entire stage of life, Then the Devonian was the time when Earth began to grow more complex. The seas were still vast. The seas were still where life was most abundant. But on land, something new was happening quietly. Bare stone surfaces, muddy margins of water, and ancient riverbanks were no longer as completely lonely as before. From small, low-lying organisms close to the ground, plants began to rise. At first, they did not look like the forests we know today. There were no dense canopies covering the sky, no rustling leaves like those heard on summer nights, no birds perched upon branches. Those first plants were still low, simple, almost humble before a vast and harsh terrestrial world. But over time, they changed. Their stems grew taller. Their internal water-conducting systems developed further. Their roots reached deeper into the soil. Lands that had once been only stone and mud began to carry a living cover. It was a very quiet revolution. Imagine you are standing beside a Devonian river long before any human being ever gave that water a name. On both banks stand ancient primitive trees, some rising much higher than a human head, growing out of the damp ground. Their roots push into the mud, touch the stone, hold the soil in place, break down minerals, and create more complex layers of earth. Each fall of rain does more than simply wet the surface. It carries with it grains of nutrients, minerals, and tiny fragments of the continent that roots and rainwater have softened, drawing them into streams, into rivers, and eventually out to sea. To the naked eye, you would only see water flowing. But in the deeper story of Earth, that water was carrying a new message from the land to the ocean, In the Devonian, plants did not merely live upon the land. They began to connect the land and the sea in a way that had never happened before. Roots made rocks weather more quickly. Soil held and released materials through new cycles. Running water carried more nutrients from the continents into the ocean. And the sea, which had been accustomed to an older biological rhythm, began receiving too much from the shore. This may sound like a gift. More nutrients, perhaps life would flourish even more. But in nature, too much of a good thing can also become imbalance. When nutrients flow into the sea algae and microorganisms can grow rapidly, they bloom in the water, spreading across wide regions, and then when they die, organic remains sink toward the bottom. There, bacteria decompose them and consume oxygen in the water. Little by little, the seafloor became suffocating. Let us return beneath the Devonian water. At first, the ocean still looks like a world full of life. This was the age of fishes. Jawed fish became more diverse. Armored fish swam through ancient waters. Early sharks appeared. Bony fish developed. Some lineages of lobe-finned fish with fins containing special bone structures would become a very important part of the long story of vertebrate life. In the shallow seas, reef communities still expanded. Ancient corals, stromatoporoids, brachiopods, trilobites, mollusks, and many marine communities together created a complex world. But beneath that richness, the balance was beginning to grow thin. Reef communities need a stable environment. They need light temperature seawater chemistry and oxygen within suitable limits. Organisms that cling in place, filter food, or attach themselves firmly to the seafloor cannot easily leave their homes. They depend on the gentle regularity of water. When the water changes, they must endure it where they are, and the Devonian Sea began to change. Not everywhere at the same time, not in one simple way, and not through a single cause that we can point to and say, this was it. The late Devonian crisis was a long and complex story. It was not like a door slamming shut in a single day. It was more like many doors slowly closing one after another over millions of years. There were major pulses of decline. There were intervals of recovery. There were marine regions that suffered heavily, while other places were affected in different ways. But when we look from a distance through the fossil record, one thing becomes clear. Devonian marine life passed through one of the greatest crises in Earth's history. In particular, shallow water reef communities suffered deeply. Picture a Devonian reef during its time of abundance. Warm water, dim blue light. Limestone structures built by living organisms rising from the sea floor. Fish swim through narrow passages. Brachiopods open their shells with the current. Trilobites crawl across the bottom. Smaller organisms attach themselves to the shells of others, forming layered, crowded, and strange communities. The entire ecosystem resembles an underwater city, built not by hands, but by time, calcium currents, and life. Then the water began to lose oxygen. We cannot see oxygen loss with the eyes the way we see a storm. It does not have a clear color in every moment. It arrives like an invisible heaviness. Creatures on the seafloor slow down. Species that need oxygen-rich water to breathe begin to weaken. Organisms that cannot move far become trapped in an environment growing more uncomfortable with each generation. A reef does not collapse with a great crashing sound. It loses one small part at a time. One species appears less often. One group is no longer found in younger rock layers. Gaps open between structures that were once crowded with life. On land, the forests were still rising. And this is what makes the Devonian story both wondrous and sorrowful. The rise of plants was one of the great advances of life. Without land, plants the later Earth would not have fertile soils, as we know them, today would not have rich terrestrial ecosystems, would not have food chains capable of supporting animals on land. Forests became the foundation for countless worlds that came after. But in the Devonian, that innovation may also have helped place pressure upon the sea. A good thing in one place can throw another place out of balance. Trees hold carbon and change the atmosphere. Roots break, rock creates soil, and draw nutrients into rivers. Rivers carry those nutrients out to the ocean. The sea responds with the bloom of tiny organisms, and then with oxygen loss in deeper waters or near the sea floor. There is no will behind this process, no guilty figure, only a planet whose systems are more tightly connected than any single living being could ever understand. That is one of the great lessons of the Devonian life is not only affected by Earth, life also changes Earth. The first forests were not merely scenery, they were a geological force. They affected rock, water, atmosphere, and sea. Each root gripping the ground was like a small finger touching the chemistry of the planet. Each rainstorm washing nutrients into rivers was like a thread linking continent to ocean. And as millions of years passed, those small effects accumulated into a change so large that marine organisms had to answer it with their very existence. Even so, we must tell this story carefully. Scientists still debate the degree to which each cause played a role. Land plants may have been an important part of the story. Volcanoes' climate shifts, changes in sea level, and ocean chemistry may also have taken part. Perhaps there was no single culprit, but many pressures together, pushing ecosystems toward their limits. The late Devonian was like a deep piece of music, with many instruments sounding at once: forests, rivers, seas, climate, volcanoes, oxygen, carbon, all blending together to create a prolonged age of instability. And within that instability, shallow marine organisms were heavily affected. Large reefs weakened, Many reef-building organisms lost the place they once held. Species living on the seafloor, dependent on stable conditions, struggled. Some ancient fish groups also suffered losses. Creatures that once dominated parts of the Devonian Sea could no longer hold their advantage forever. Meanwhile, other groups more flexible or living in environments less affected continued on. Imagine a large armored fish moving through murky water, its heavy body covered in natural plates. It was an impressive creature of its age, a mark of the Devonian Sea. But history does not forever favor forms that once seemed powerful. When the environment changes, old strength is not always the new answer. Large bodies, specialized lifestyles, and narrow environmental needs can become burdens. Meanwhile, in other waters, smaller and more flexible fish lineages continued through the crisis. Some organisms could tolerate lower oxygen conditions. Some lived where water circulated better. Some did not depend entirely on shallow reefs, and on land plants and other small organisms continued to expand their new world. This is not a simple story of life being defeated. It is the story of the harsh selection imposed by the environment. When the world changes its rhythm, each species must answer with its body, with its way of feeding, with its habitat, with its capacity to endure. And no answer remains correct forever. In late Devonian rock layers, the change appears as a chain of traces. In some places, there are black rocks suggesting oxygen-poor waters. In some places, reef groups decline. In some places, fossils disappear after a certain boundary. Those slabs of stone do not speak in words, but if we listen long enough, they tell of a sea that once flourished and then was forced to change. And here, let us pause for a moment to feel the depth of time. A reef community can take thousands of years to grow. A marine ecosystem can remain stable across countless generations. An evolutionary lineage can exist longer than the entire history of humankind, many times over. Yet in the geological record, it can still enter a passage of decline. Not because it was weak, but because the planet it depended on had changed too much. We often think of survival as a powerful act. But in the Devonian, survival may have meant simply continuing to exist in a patch of water with slightly more oxygen. It may have meant being able to move a little farther. It may have meant being able to eat a slightly wider range of food. It may have meant reproducing quickly enough to pass through the worst intervals. Life did not overcome crisis through splendor. It overcame it through small, quiet, sometimes very humble advantages. After the pulses of crisis, the Devonian Sea was no longer the Devonian Sea that had existed before. Ancient reef communities did not return intact. Groups that had once played major roles were reduced or disappeared, but life did not stop. Surviving groups continued to spread, adapt, and open the way for other ecosystems in the future. On land, plants continued writing a new chapter for the planet. The once bare lands increasingly held root soil shelter and more living relationships. There is a very deep beauty in that paradox. Forests helped make Earth more like a world capable of supporting rich life on land. But the very changes created by forests may also have helped drive the Devonian Sea into crisis. An evolutionary advance opened the door to the future while shaking the present. A triumph on land became a trial in the ocean. Earth does not operate like a story with good characters and bad characters. It operates like a vast system where everything touches everything else in slow but profound ways. If the Ordovician taught us that ice and sea level could change the stage of life, then the Devonian teaches us that life itself can become a force capable of redirecting the planet. Imagine a Devonian evening in the far depths of time. Sunlight falls across a primitive forest. There is no bird song. No animal runs across the leaf litter. Only strange trunks, damp riverbanks, small creatures crawling through newly formed soil, and a current of water quietly carrying nutrients toward the sea. Far offshore, beneath the water, an ancient reef is weakening in waters increasingly poor in oxygen. Those two scenes, the forest on land and the sea far away, seem separate. But in truth, they are linked by an invisible thread. The river is that thread. It carries the story of the land to the sea. It carries minerals, mud, organic matter, nutrients. It tells the ocean that the land has changed. And the ocean, after millions of years, answers with a biological crisis. As the Devonian chapter closes, we do not leave with the feeling that everything has ended. We leave with the feeling that Earth has become more complex. Life is no longer only in the sea. The land has begun to have a voice. Forests have appeared as a new force. The ocean has been affected by what happens on shore. The ecosystems of the planet have become more tightly linked together, and therefore they can also wound one another more deeply. That is the mystery of the Devonian, an age radiant with fish, with reefs, with the first forests, but also an age in which the seas changed forever. The surviving creatures stepped onward into the world after the Devonian, carrying within their bodies the memory of a sea that had once lacked oxygen, a reef that had once declined, and a planet that had learned that trees could alter climate and ocean. From here, life would continue to expand. It would continue to experiment. It would continue to build. But ahead, in an even more distant age, Earth would face a trial far greater in scale. Before we arrive there, hold on to the final image of this chapter. An ancient forest stands still beside a river. Roots grip deeply into new soil. Water flows through mud, through stone, through lands that had never known the shadow of trees before. The river moves toward the sea, carrying the traces of a changing world. And beneath the distant water, the Devonian ocean, once filled with cities of reef life, begins to breathe with difficulty in the deep blue darkness. It was not the end of life. It was once again life being forced to learn how to exist on an Earth that was no longer the same. After the Devonian period, life continued to move through time like a long river. The marine reefs had changed. The first forests had begun to set their footprints upon the land. The ocean was no longer the only stage of life. Earth had become more complex, greener, more layered, and in a very profound way, more fragile. Then tens of millions more years passed. The continents continued to drift. Seas opened and then closed. Mountains rose, were worn down by rain and wind, and left sediment behind for lower regions. Forests spread across the land. Insects appeared in the air. Four-limbed animals evolved into many different forms. Some lived near water. Some moved deeper into the interior. Some carried strange shapes like the first experiments of life upon the land. And then Earth entered the Permian period. If you could look at the planet from far away during the late Permian, you would see a world very different from today. Most of the continents had joined together into one enormous supercontinent, Pangaea. A vast mass of land stretched from north to south, surrounded by a boundless ocean. From above, Pangaea would look like a continent too large for its own climate. Along the coasts, life may have been rich, but deep within the interior, far from the moisture of the ocean, many regions became dry, hot, harsh, and almost overwhelming in their vastness. Imagine you are standing on a Permian landscape at sunset. Before you lies a dry plain rivers winding through red mud, ancient shrubs and scattered forests of seed plants. There is no familiar birdsong like today, no bright flowers blooming across the grasslands. Instead, it is a world of strange living beings, ancient reptiles, distant relatives of mammals, creatures with forms both familiar and unfamiliar, as if Earth were trying out many different sketches for the future. Beneath the sea, life had also built ancient communities. Brachiopods, crinoids, mollusks, ammonoids, ancient corals, and many groups of marine invertebrates had passed through long eras. And especially trilobites, the famous inhabitants of ancient seas, still existed after hundreds of millions of years. They had passed through earlier upheavals. They had once survived retreating seas, changing climates, and declining reefs. But in the late Permian, even such enduring lineages were about to step into their greatest trial. Something began to happen in the region we now call Siberia. It was not a single volcano erupting for a few days. It was not a brief spectacle that quickly ended. It was a chain of volcanic activity on an enormous scale, lasting through geological time, creating vast flows of basalt. Lava spread out. Gases rose into the sky. Carbon dioxide, sulfur dioxide, and many other gases entered the atmosphere. The planet began to receive an impact too large, too prolonged, and too deeply embedded in the climate and ocean systems. Imagine the sky somewhere far across Pangaea. It did not necessarily glow red at all times, like an eruption unfolding directly before the eyes. In many places, the change may have come more indirectly. Hot seasons grew longer, the air became drier. Rain may have become irregular, the seas gradually warmed, currents changed, deep waters slowly lost oxygen. The chemistry of the ocean was no longer as stable as before. This is what makes the Permian-Triassic extinction frightening in such a slow way. It was not only a single event, it was a chain of crises linked together. Volcanoes changed the atmosphere. The atmosphere changed the climate. The climate changed the ocean. The changing ocean weakened underwater chains of life. On land temperature, drought, rainy seasons, wildfires, habitats, and sources of food were also overturned. When a great system like Earth is pushed out of balance, everything begins to touch everything else. The Permian Sea did not merely become warmer. When seawater warms, it holds less oxygen. When ocean currents weaken or change oxygen from the surface, has more difficulty reaching deeper layers. Oxygen-poor waters can spread. For organisms living on the seafloor, that is almost impossible to escape. They cannot run onto land. They cannot fly away. They cannot simply wait for a better season if the entire environment around them has changed across many generations. Let us return to a late Permian seafloor. This place was once crowded with life. The shells of brachiopods opened into the current. Crinoids stretched their soft arms through the flowing water. Trilobites crawled slowly across the mud. Ammonoids moved through the water column. But then the water grew heavier, warmer, and poorer in oxygen. Creatures that required stable conditions began to weaken. Ancient reefs slowly lost their vitality. Many groups no longer appeared in younger rock layers. A marine world that had lasted for millions of years began to thin out like the final light of evening. And when the ocean had already begun to struggle for breath, another problem appeared: acidification. As the amount of carbon dioxide in the atmosphere increased, part of it dissolved into the seawater. The chemistry of the ocean changed. For organisms that needed to build shells or skeletons from carbonate minerals that change, place them under great pressure. Bodies that had once been protective advantages now became harder to build, harder to maintain. Marine communities that depended on delicate chemical balance were placed in a new world where the very water around them was no longer as welcoming as before. Here we can feel the harshness of the crisis, not through an explosion, but through a very fundamental change. Water, the very thing that supported life, became a more difficult environment in which to survive. On land, Pangaea was not gentle either. A gigantic supercontinent has interior regions very far from the sea. Such places can be dry, hot, and strongly seasonal. When the global climate was pushed into instability, places that were already harsh became even harder to live in. Plants came under pressure. When plants declined, herbivores lost their source of food. When herbivores declined, predators were pulled down with them. No ecosystem stands alone. Every creature is a link within a web, and when too many links are stretched at once, the whole web can begin to tear. Picture a late Permian plain. An ancient plant-eating animal walks across cracked ground. It searches for the familiar vegetation it once knew, but the green regions have grown thinner. Streams are shallower. The dry season is longer. In the distance, the sky may be hazy with dust gas or smoke from natural fires. The creatures on land do not understand the cause. They simply live through each day, searching for shelter, searching for food, searching for water, in a world that is becoming more and more difficult to predict. Not every place was the same. Not every living being endured the same pressure. But on a planetary scale, the change was immense. The late Permian did not wound only the sea. It also transformed the land in deep ways. Life was tested on both of its greatest stages. And then in the fossil record, the Permian-Triassic boundary appears as one of the sharpest cuts ever recorded. Below that boundary lies the world of the Paleozoic, the ancient era of life with long-established marine communities and groups of organisms that had once dominated for hundreds of millions of years. Above that boundary lies the Mesozoic, a newer and stranger world where the survivors had to rebuild ecosystems almost from the beginning. Between those two worlds lay an enormous absence. Trilobite symbols of the ancient seas disappeared completely. Ancient corals such as rugose and tabulate corals did not continue. Many groups of brachiopods declined severely. Crinoids, bryozoans, ammonoids, and many other marine animals suffered deeply. On land, many branches of four-limbed animals also failed to pass through this period. Life was not erased from Earth, but its face had been changed so profoundly that it was almost unrecognizable. This is why the Permian-Triassic extinction is often considered the greatest biological disaster in the history of Earth. But in a bedtime documentary, we do not need to turn this chapter into a noisy spectacle. Its weight lies in the silence afterward. Imagine a seafloor after the crisis. Fewer shells, fewer crawling traces, fewer reef structures. A place that had once been crowded now becomes open and empty. Sediment still falls. Waves still pass above. The sun still rises over the water. But the communities that had made the sea rich for millions of years are no longer there as before. On land, it was the same. Ecosystems did not recover immediately. After the late Permian, life entered a slow and unstable period of recovery. It is not the case that once disaster passes, the world becomes green again in a single season. Sometimes a planet needs millions of years to rebuild balance. Empty land species, poor communities, and simpler food chains can persist for a very long time before true diversity returns. And in that post-Permian world, the survivors were not necessarily the most majestic creatures. Some species survived because they were smaller, less selective, and more resilient. Some could eat many different sources of food. Some could dig burrows, take shelter, or reproduce in ways that helped them endure harsh environments. Some organisms had not dominated the old world, but they were better suited to a world that had been remade. One name, often mentioned in the period after the Permian, is Lystrosaurus, a distant relative of mammals, with a sturdy body, a beak-like mouth, and an ability to live very successfully in early Triassic ecosystems. It was not a magnificent creature in the usual imagination, but its abundance in post-crisis rock layers reveals something profound. After great upheavals, Earth does not offer opportunity to the most beautiful or the most powerful species, but to the species best suited to the conditions that remain. That is a lesson repeated again and again in the history of life. Survival is not always a resounding victory. Sometimes survival means simply being able to tolerate a little more heat, a little more dryness, a little longer without food. Sometimes it means being able to live in more than one environment. Sometimes it means being able to bring a new generation into the world before the worst conditions return. Small advantages that may not stand out in peaceful times can become the boundary between continuation and disappearance during a crisis. The Permian-Triassic extinction also reminds us that Earth has more than one way to shake life. The Ordovician was tied to ice and sea levels. The Devonian was tied to oxygen-poor seas, the first forests, and complex changes between land and ocean. But the Permian-Triassic was a wider picture where volcanoes, climate, atmosphere, ocean, and continent all pulled one another into a cycle of upheaval. It was like many waves striking a weakened shore at once. One wave may not have been enough, but many together can change the shape of the entire coastline. In the late Permian, life did not face a simple question. It did not only have to endure heat. It did not only have to endure oxygen-poor seas. It did not only have to endure acidification, drought, wildfires, sea level change, or loss of habitat. It had to endure many of these things at the same time in a vast world where natural systems were falling out of balance. So, when we look at a Permian fossil, we should not see only an old creature. We should see an inhabitant of a world that had come very close to its limits. A brachiopod shell is not only a shell. It is the trace of a sea that once had oxygen currents, food, and living space. A footprint in stone is not only a footprint. It is the moment a creature crossed the Permian landscape, unaware that its age was closing. There is a very quiet sorrow in those traces, not sorrow in the way human beings mourn, because there was no one there yet to tell the story. No one to lay flowers for the species that were lost. No one to name an old world. Only stone remembered. Only layers of sediment preserved the boundary between before and after. Only time, patient to the point of coldness, placed everything into the earth so that hundreds of millions of years later, we could understand that there had once been a moment when life on Earth was tested at its deepest level. But this chapter does not end with emptiness, because although the Permian-Triassic extinction is the greatest known biological disaster, life still did not stop. Some species remained. Some evolutionary lineages continued. Some small, enduring, flexible organisms lived on in the narrow spaces of the post-crisis world. And from those remaining fragments, Earth began to build a new age. Not quickly, not easily, not like a spring arriving immediately after a long night. Recovery after the Permian was a slow journey, perhaps stretching across millions of years. But eventually, new ecosystems formed. New groups of organisms stepped onto the stage. the oceans filled with different communities. The land began to prepare for the changes that would open in the Triassic period. As we leave the Permian-Triassic chapter, carry with you one slow image, a vast supercontinent beneath a hot sky. Far to the north, enormous basalt regions continue to bear the marks of volcanic activity. Offshore warm and oxygen-poor waters cover seafloors that were once crowded with living creatures. On land, the remaining species move through a world with less green shade, drier, stranger than before. And in all that emptiness, life still holds a few very small whispers. Those whispers would become the beginning of the next chapter, after the Permian Earth entered the Triassic. An old world had been pushed back. A new world had not yet become stable. The survivors crossed the thin boundary between two ages, unaware that ahead of them, in the recovering landscapes, another group of creatures would slowly prepare for its rise. It was not yet the complete age of dinosaurs, but the first door had begun to open. After the Permian-Triassic crisis, Earth did not recover at once like a green forest returning after the rain. It entered the Triassic period with a body still carrying many wounds. The ocean had lost many of its ancient inhabitants. The land no longer resembled the old world of the Permian. Once stable communities of life were replaced by simpler, stranger ecosystems, as if the planet had to learn all over again how to nourish life from the beginning. But life continued. Across the immense supercontinent of Pangaea, the surviving creatures began to spread through a harsh world. The climate in many regions was hot and dry. Inland areas far from the sea could pass through long seasons of drought. Rivers changed with the seasons. In some places, there were red plains covered with dust. In others, there were more humid coastal regions where plants and animals had greater chances to survive. All of this created an Earth that was both empty and full of possibility. The Triassic was not the age of dinosaur domination from the very beginning. This is very important. When we hear the word dinosaurs, we often think of gigantic shadows covering the land, long-necked herbivores walking through forests, and great predators leaving deep footprints in the mud. But through much of the Triassic period, dinosaurs were only one among many groups trying to find their place on the stage of land life. They had appeared, but they were not yet the absolute rulers of the planet. Alongside them were many other ancient reptile groups. There were powerful relatives of crocodiles with strong bodies and commanding movement occupying important predatory roles. There were large plant-eating reptiles. There were great amphibians living near water. There were smaller creatures, distant relatives of mammals, quietly surviving in the shadows of larger groups. In the sky, the first flying reptiles began writing their own story. Beneath the sea, marine reptiles also expanded through oceans that were still recovering. It was not a simple world. It was not a world where dinosaurs were merely waiting to step onto a throne already prepared for them. It was a world of competition, experimentation, and many different evolutionary branches, each one searching for a place of its own. Imagine a Triassic afternoon on Pangaea. The sun falls across a river plain. Dry mud cracks into long lines. In the distance, seed plants and ferns grow in scattered clusters. An ancient reptile moves along the water's edge, its body low but strong, its eyes watching small movements in the brush. A group of herbivorous creatures lower their heads to search for young leaves. Somewhere in the shade, a small, agile dinosaur moves lightly across the ground, not yet knowing how vast the future of its lineage will become. At that moment, there was no sign that dinosaurs were certain to dominate. History had no signposts set in place. No creature was promised in advance that it would become heir to the world. Everything depended on the environment, on competition, on the ability to adapt, and sometimes on great upheavals that changed the entire board. Then at the end of the Triassic period, that board began to tremble. Pangaea, the enormous supercontinent, did not keep its solid shape forever. Deep within it, forces from inside Earth began to stretch the continental crust. Great cracks opened. Huge landmasses prepared to separate. This was the early stage in the formation of the Atlantic Ocean. But before a new ocean truly widened, Earth passed through a period of volcanic activity on a massive scale. Along the rift zones of Pangaea, magma rose. Not as a single lonely volcano of the kind we often imagine. This was a vast magmatic province where basalt flows erupted across enormous areas. This activity occurred in several pulses, not necessarily as one single scene continuing without pause, but it was large enough to leave traces in rocks found in many places today. Gases were released into the atmosphere. Carbon dioxide increased. Sulfur compounds and many other substances may have contributed to environmental instability. The climate warmed. The ocean absorbed some of the carbon dioxide, altering the chemistry of seawater. Some marine regions may have become more acidic. Oxygen in the water declined in many areas. On land, temperature, rainfall, dry seasons, and vegetation all came under pressure. Once again, Earth did not suffer only one simple blow. It endured a chain of connected changes. The atmosphere changed, and the climate changed. The climate changed, and forests and rivers changed. The ocean changed, and marine life came under pressure. The land changed, and food chains began to tremble. Life did not face one closing door, but many doors slowly closing together. Let us descend into a late Triassic sea. There, reef communities, mollusks, brachiopods, corals, and many marine invertebrates are living in their own ecosystems. The seawater may still seem vast, still moving with the tides, still reflecting sunlight. But within its invisible chemistry, something is changing. As the ocean warms, dissolved oxygen can decrease. As the water becomes more acidic, organisms that build shells or carbonate skeletons struggle. Species that cling in place, move little, or depend on stable conditions have few ways to escape such pressure. A reef does not break apart like a building collapsing. It weakens little by little. One group of organisms disappears from one region. One species no longer appears in the rock layer above. Structures that were once crowded become thinner. The current still passes through, but the old inhabitants are no longer numerous enough to hold the same rhythm of life. On land, the change was no less profound. Many large reptile groups and four-limbed animals that had once been important in Triassic ecosystems were heavily affected. Some lineages did not cross the boundary into the Jurassic period. Creatures that had competed with dinosaurs in many ecological niches declined or disappeared. Forests also changed. Vegetation in many places was reorganized. Living communities that had once been familiar with the conditions of the late Triassic now faced a planet that was hotter, more unstable, and harder to predict. In that context, dinosaurs did not simply appear from nowhere. They had already been present. But the end Triassic extinction changed the world around them in a powerful way. Many ecological competitors were removed from the stage. Many empty spaces opened. Roles within ecosystems that had once belonged to other groups were now left unoccupied. And in those spaces, the surviving dinosaur lineages had the opportunity to spread. This is the point that must be told with care. The Triassic extinction did not create dinosaurs. It did not give birth to them in a single moment. But it changed the world in a way that allowed dinosaurs to move from being one group among many into an increasingly prominent force during the Jurassic period that followed. Imagine the stage of life as a wide landscape with many roads. Before the crisis, dinosaurs were moving along only some smaller paths. Other groups held the larger routes, the richer food sources, and the greater opportunities. But after the upheaval at the end of the Triassic, some of those roads suddenly became empty. Agile, well-adapted survivors could step into those open spaces, and once they had stepped in, they began to diversify, grow larger, spread outward, and gradually become the symbol of the next age. In the long story of Earth, sometimes a dynasty does not begin with a coronation. It begins with an emptiness. After the end of the Triassic, that emptiness was vast. Early Jurassic dinosaurs did not immediately transform into the giants so familiar in our imagination. That expansion needed time. But the door had opened. Faster carnivorous species appeared. Herbivorous species developed in different directions. Dinosaur bodies experimented with size, posture, feeding, and ways of life. From the lineages that survived the crisis, an age lasting more than 100 million years began to take shape. And this gives the Triassic chapter a very special color. It is both a story of loss and a story of transition. Not as dark as the late Permian, where life was pushed to its deepest limit. Not as cinematic as the end of the Cretaceous, where an event from the sky would close the reign of the non-avian dinosaurs. The end of the Triassic is like a long sunset of an old world where ancient groups of life quietly leave the stage, while far away the first light of a new age begins to rise. If we could stand upon Pangaea after that crisis, the world would probably not appear glorious at once. It may still have been harsh. Many places remained unstable. Ecosystems had not yet filled themselves again. Gaps in the food chains were still wide. But within that unfinished world, the future began to form. A small dinosaur passes along the riverbank. It is not large, not majestic, not like a symbol of power. But it belongs to a surviving lineage. Its body is light. Its legs are positioned beneath its body, helping it move efficiently. Its rhythm of life is better suited to certain new conditions. It does not need to know that after it there will be giants lifting their necks among Jurassic forests, predators leaving deep footprints, herds of herbivores crossing continents like living mountains. It only needs to survive one more day. And from days like that, history is built. Life after every extinction never returns with a grand declaration. It returns through the creatures that remain, through new generations, through small experiments. One species finds food somewhere else. One group adapts to a new climate. One body becomes better suited to a new way of moving. One evolutionary lineage takes over an empty ecological niche. Then across millions of years, those small things become an age. The Triassic extinction was therefore a major turning point in the history of life. It marked the end of many Triassic communities, but it also opened the beginning of the Jurassic world. And the Jurassic world would be where dinosaurs truly stepped into the role we still remember today. Great creatures of the land, gigantic shadows, imprinted deeply in the imagination of humankind. But before leaving this chapter, let us return to the first image, Pangaea beginning to split apart. Deep below the ground, magma rises. On the surface, lava flows across wide regions. The atmosphere receives gases from deep within the planet. Ocean chemistry changes. Reef communities weaken. Ancient reptile groups on land lose their place. And amid all those upheavals, the remaining dinosaur lineages cross the Triassic-Jurassic boundary. They were not victors in a conscious war. They were the ones better suited to the world after the board had been overturned. That is something both cold and wondrous in the history of Earth. No throne is granted forever. No group of organisms dominates because of destiny. Every dynasty of life stands upon fragile conditions. Climate, sea forests, oxygen, food habitat, and countless small connections that a great change can shake apart. At the end of the Triassic, Earth changed those conditions. and dinosaurs, from creatures that had not yet truly dominated, began to step into the empty space left behind by the crisis. As this chapter closes, hold on to one image: still and vast, an early Jurassic land after a long night of upheaval. The air is still warm. A river flows quietly across ancient mud. Seed plants stand in the morning light. Far away, a small creature runs along the water's edge, leaving slender footprints in the soft ground. Those footprints may be erased by rain. They may be covered by mud. They may turn to stone and lie still for hundreds of millions of years. But within those small footprints is the beginning of an age. From the empty spaces after the Triassic extinction, the world of dinosaurs began to open. And across the millions of years that followed, Earth would witness one of the most magnificent dynasties of life ever to exist upon land. But like every dynasty in the history of life, it would not last forever. Ahead, on a very distant day, the sky would bring another upheaval. And this time, the dinosaur world itself, once opened by the aftermath of the Triassic, would have to face its greatest trial. After the extinction at the end of the Triassic, the door to the age of dinosaurs had opened. From creatures that had once been only one branch among many survivors on land, dinosaurs gradually stepped onto Earth's great stage. Through the Jurassic and then into the Cretaceous, they spread, diversified, and transformed into countless different forms. There were species that stood tall like living towers, moving through forests. There were carnivores with heavy footsteps and sharp teeth. There were small, fast, lightweight species covered in feathers, moving through the shade of trees or across lowland regions. There were species that lived in herds, leaf-eaters, hunters, creatures with horns, armor, beaks, and crests. For more than 100 million years, dinosaurs did not merely exist. They became a profound part of the planet. But as we have seen in the previous chapters, no dynasty of life is guaranteed forever. The Ordovician Ocean had once been filled with living creatures before falling into crisis. Devonian reefs had once flourished, then weakened in oxygen-poor seas. The Permian world had once held enduring lineages, yet even they did not survive the greatest disaster. The Triassic had opened the way for dinosaurs, but that very opening was also born from loss. Earth's history is not a straight path upward. It is a long road interrupted again and again by events greater than any species could resist. And then, at the end of the Cretaceous, such an event came for the world of dinosaurs. Let us begin slowly, not with the sound of impact, but with an ordinary morning about 66 million years ago. The sun rose over an Earth warmer than today. The continents had taken shapes closer to the modern world, though still different. Inland seas covered certain regions. Flowering forests had developed strongly, carrying with them insects, pollen fruit, and seeds. Plant species more familiar to us were beginning to appear in ancient landscapes. Birds were already present in the sky, though not like the rich bird world of today. Mammals also existed, most of them still small, living quietly in the shadows of larger creatures. On a riverside plain, a herd of herbivorous dinosaurs may have been moving through damp ground, their footprints pressed into soft mud. Far away, a large predator stood in the morning light, not hurrying, only watching the world as it had always watched it. Insects flew among ancient flowers. Turtles crawled near the water's edge. Crocodiles lay motionless along the riverbank. In the ocean, coiled ammonites swam through the water, marine reptiles hunted offshore, and tiny plankton drifted in the light. There was no sign on the ground that this morning belonged to the ending of an age. But in outer space, a gigantic object was approaching. It may have wandered through the solar system for a very long time before its path crossed Earth's orbit. An asteroid large enough to alter the global climate entered the planet at a terrifying speed. For the creatures below, there was no time to understand, no time to leave, no time to look upward and grasp the meaning of the light growing larger in the sky. Then it struck the region we now know as the Yucatan Peninsula in Mexico. That moment did not merely create an impact crater. It released energy far beyond anything life on the ground had ever experienced. Rock was crushed and vaporized. The ground shook. Shock waves spread outward. A gigantic crater formed at the place of impact, later called Chicxulub by human beings. Material from the ground and from the asteroid itself was thrown into the atmosphere. Dust, hot rock, water vapor, sulfur, and many other substances rose high into the sky, then spread across the planet. Across a vast region around the impact site, the scene may have been almost impossible to imagine. Earthquakes, tsunamis, scorching winds, flying rock seawater pushed into enormous walls. But what truly made this event a global mass extinction did not lie only in the impact region. It lay in what happened afterward, when the atmosphere of the entire planet was changed. Hot fragments of material fell back through the atmosphere, setting the sky ablaze for a time. Many regions may have endured wildfires. Ash dust and fine particles spread widely. Sunlight was dimmed. Temperature and climate entered extreme disturbance. In the oceans and on land, food chains began to suffer from their very foundations. Imagine a post-impact world not as one single scene, but as a long sequence of abnormal days. The sky was no longer clear as before. The light weakened. The sun may have appeared only as a dim disk behind layers of dust and gas. Plants did not receive enough light. Photosynthesis declined. Plant life weakened. When plants declined, herbivores lost their food source. When herbivores declined, predators were pulled down with them. An ecosystem does not collapse only from the top. It collapses from its foundations. Beneath the sea, the same thing unfolded in the ocean's own way. Photosynthetic plankton formed the foundation of many marine food chains. If the light declined, those tiny organisms were affected first. Yet those small organisms nourished an entire vast world above them. When the foundation trembled, the creatures that fed upon them also declined. Then the creatures that fed upon those creatures were affected in turn. From organisms too small to see with the naked eye, the crisis spread upward to fish marine reptiles, ammonites, and larger communities. Ammonites are one of the saddest images of the end of the Cretaceous. They had existed for a very long time, with their beautifully coiled shells, like ancient symbols of the ocean. They had endured many upheavals in Earth's history, diverse and successful in many seas. But after the Cretaceous boundary, they did not continue. Their fossil shells remained in stone like the final spiral of a lineage that had once been magnificent. On land, non-avian dinosaurs faced a world that changed too quickly and too deeply. Large species needed great amounts of food. Herbivorous species depended on vegetation. Carnivorous species depended on prey. When the sky darkened, when plants declined, when food chains were severed, large size was no longer an absolute advantage. Strength cannot help a species endure if the entire source of its life has been taken away. Imagine a large herbivorous dinosaur after the event. It walks across a dust-covered land searching for fresh leaves as it had in earlier seasons. But the trees are thinner. Burned or devastated regions leave the landscape open and empty. The remaining plants weaken under the dim light. That animal does not understand the atmosphere. It does not understand the Chicxulub crater. It does not understand sulfur dust or the collapse of food chains. It only knows hunger, exhaustion, and a familiar world becoming unrecognizable. And the great predators, no matter how powerful, were also bound to the survival of their prey. A biological empire does not exist because of one species alone. It exists through countless connections. When herbivores declined, predators gradually lost their foundation. When eggs young shelter vegetation and water sources were all affected, future generations also became more fragile. The end of the Cretaceous did not merely end a few famous dinosaur species, it ended all non-avian dinosaur lineages. Creatures that had dominated the land for so long disappeared from the younger rock layers. The great footprints did not continue into the world that followed. The roars we imagine when looking at fossils retreated into the silence of stone. But one important thing must be kept very clear. Dinosaurs did not disappear completely. Birds are the living descendants of theropod dinosaurs. This makes the end Cretaceous story much deeper. A part of the dinosaur world crossed that boundary not in the form of giant flightless creatures, but in smaller, lighter bodies with feathers, with the ability to fly, or with more flexible food sources. When a bird sings outside the window today, that sound is a very distant echo of a dinosaur lineage that passed through the narrow doorway of time. Of course, not all ancient birds survived. Many bird lineages also disappeared, but some lineages crossed through enough to later open the immense diversity of modern birds. This once again reminds us that survival is never simple. Not every small group survives. Not every large group is unable to pass through. But in the context after the impact, traits such as small body size, the ability to take shelter, a flexible diet, suitable reproduction, and less dependence on collapsing food chains could become major advantages. Mammals also crossed that boundary in a quiet way. During the age of dinosaurs, they were not the creatures that dominated the land. Many species were small, nocturnal burrowing, or hidden within vegetation. But those very humble ways of life may have helped some groups pass through the harsh period. They did not require enormous amounts of food like larger species. Some could eat insects, seeds, organic remains, or many other food sources. Some could shelter in burrows, avoiding part of the harsh conditions on the surface. Turtles, crocodiles, amphibians, fish, insects, and many other groups also had surviving lineages. Each group carried its own story. Some species were protected by freshwater environments. Some endured periods without food better than others. Some depended less on fresh vegetation. Some had life cycles, shelters, or reproductive strategies that helped them hold on through the age of chaos. But this chapter is not yet the place to go deeply into all those paths of survival. We will save that for the next chapter when we look at how life rebuilt Earth after the 5 great mass extinctions. Here, what matters is to feel the moment of transition at the end of the Cretaceous. An old world closed, but not all life was erased. A few small flames still burned in the darkness. And perhaps it is precisely that contrast that makes this event so haunting. An asteroid fell, and in a very short span of geological time, the biological history of the planet was bent in a different direction. If that object had missed by a little, if it had fallen somewhere else, if the composition of the rock at the impact site had been different, the history of life may have been different. But it fell where it fell. It struck a region of rock capable of releasing enormous amounts of material into the atmosphere, and the result was one of the most famous extinctions of all time. This story was not only about the asteroid. At the end of the Cretaceous, Earth may also have been under additional pressures, including the Deccan volcanic activity in India. Those great eruptions also released gases into the atmosphere and may have contributed to climatic instability. But within the larger picture of the end Cretaceous event, The evidence for the Chicxulub impact remains the central clear and powerful marker connected to the sudden disappearance of many groups of organisms at this boundary. Imagine a geologist, tens of millions of years later, standing before a thin layer of stone lying between two ages. In that layer are signs of rare material of grains shocked by impact of an event unlike the ordinary changes of sea or climate. Below it is the world of non-avian dinosaurs, ammonites, marine reptiles, and many Cretaceous communities. Above it is a world that was poorer. At first, then gradually opened the way for surviving organisms to develop in new directions. A thin line in stone, yet it divides an empire in two. That is what makes the fossil record both cold and beautiful. It does not preserve the roar. It does not preserve the fear. It does not preserve one final morning as a living memory. But it preserves enough traces for us to understand that there was once a time when the sky changed the fate of the ground. After the impact, time continued. The dust slowly settled. Light returned. Plants gradually recovered where they could. New ecosystems, at first poor and scattered, began to form. Earth did not immediately become green and abundant as before, but it also did not remain silent forever. In cracks and small burrows in freshwater regions, in surviving branches, in seeds, in small creatures that knew how to wait, the future still remained. The non-avian dinosaurs had left the stage, but birds continued to fly, mammals continued to live, flowering plants continued to spread, insects continued to adapt, the ocean began to rebuild its food chains. And from what remained after the Cretaceous boundary, a new world would slowly emerge, the world that would eventually lead to us. The first image is the sky at the end of the Cretaceous, where a strange light rushed downward and shook the entire planet. The second image is much smaller. A tiny creature, perhaps a small mammal in a burrow, or an ancient bird perched in the shadow of a tree, living through a long night it did not understand. It did not know that the gigantic creatures around it were disappearing from the future. It did not know that later the descendants of the survivors would fill the empty spaces of Earth. It only knew to keep breathing, to keep searching for food, to keep taking shelter, to keep living. And sometimes in the deep history of the planet, that alone was enough for a new world to begin. The end of the Cretaceous was the ending of the empire of non-avian dinosaurs, but it was also the doorway opening for the silent heirs. After 5 great mass extinctions, the greatest question finally returns to us. Why is life still here? Why, after ice, oxygen, poor seas, volcanoes, harsh climates, and asteroids, did Earth not become an empty planet? After the 5 great mass extinctions, perhaps what astonishes us most is not only what was lost, but what still remained. Earth has passed through frozen ages when the sea retreated from the shallows and carried entire ancient communities of life away with it. It has witnessed oxygen-poor seas where reef communities struggled to breathe in the deep blue darkness. It has endured immense crises in which volcanoes, climate, atmosphere, and ocean all changed together. It has been marked by an asteroid from space, leaving a deep scar upon its surface and bringing the reign of the non-avian dinosaurs to an end. And yet after all of that, life is still here. Not the old life exactly as it was. Not the same creatures, the same reefs, the same forests, the same rulers. After each time Earth was pushed beyond a great threshold, life did not return to its original state. It came back with a different face, a different form, a different order. The survivors stepped out of the darkness, then slowly filled the world in ways no one could have predicted before. That is what makes the history of life both fragile and wondrous. Imagine a morning long after an extinction. There is no sound of triumph, no scene in which the world instantly turns green again. No clear moment that says from this day forward, life has recovered. Instead, there is a very small beginning. One remaining species finds a place to shelter. A seed germinates on an empty patch of ground. A small creature crawls out of its burrow when the sky has grown brighter. A marine lineage persists in waters that still hold enough oxygen. A new generation is born into a poorer, quieter world, but one that still contains possibility. Life did not rebuild Earth through the strength of a single species. It rebuilt it through countless small acts repeated across thousands, across millions of years. After extinctions, the world often becomes emptier. Groups that once held major positions within ecosystems have disappeared or declined. Ecological niches, meaning the living roles within nature, are left vacant. Where there was once a large plant-eating group, there is now an empty space. Where there was once a dominant predator, there is now an empty space. Where there was once a crowded reef, there are now sparser seafloors. And those empty spaces become opportunities for the groups that remain. But opportunity is not an easy gift. A world after extinction is often not stable right away. The climate may still be changing. The ocean may not yet have fully recovered. Food chains may still be broken. The surviving species do not step into a new paradise. They step into a world of absence hardship, many openings, but also many risks. To expand, they must endure, adapt, reproduce, find food, avoid new competitors, and pass through the disruptions that may continue long after the crisis. So survival is only the first step. Rebuilding the world is a much longer journey. After the Ordovician extinction, the ocean did not recover in a single moment. The remaining marine groups had to spread through waters that had changed. Some lineages continued to exist. New communities gradually formed. The sea did not return exactly as it had been, but it filled again with different forms. From the creatures that survived across the Ordovician-Silurian boundary, marine ecosystems continued writing their history. After the Devonian, when ancient reefs had been deeply wounded, the ocean also had to reorganize itself. Reef communities no longer kept their old appearance. Groups that had once been important diminished, while others found new places. And on land, forests continued to expand, soil continued to form, and rivers continued to carry the story of the continents out to sea. Life did not only heal the ocean, it also transformed the land into an increasingly rich stage. After the Permian-Triassic extinction, the rebuilding process was far more difficult. This was the greatest biological disaster life had ever faced, so recovery could not happen quickly. Early post-Permian ecosystems may have been species-poor, simple, and vulnerable. But within that impoverished world, the survivors began to expand. Some organisms were better able to endure harsh conditions. Some could eat a wider range of food. Some could live in more than one environment. From those remaining lineages, the Triassic period gradually formed new communities. After the Triassic, when many ancient reptile groups declined or disappeared, dinosaurs had the chance to expand powerfully. They were not born from that extinction, but the extinction changed the world around them. Vacant ecological niches became roads. Surviving dinosaur lineages stepped into the Jurassic period and gradually developed into one of the most famous dynasties of life in Earth's history. After the Cretaceous, when the non-avian dinosaurs vanished, Earth entered yet another new chapter. Mammals, Once small creatures living in the shadows of larger beings began to expand. Birds, the living descendants of dinosaurs, continued to diversify. Flowering plants spread even farther. Insects, birds, mammals, and plants began forming new relationships. From the post-asteroid world, forests, grasslands, oceans, and ecosystems would eventually appear, leading to the world we live in today. Looking back across that entire journey, we see that life did not have one single secret for surviving the great mass extinctions. It had many paths. Some species survived because they were small. A small body helps an organism need less food, hide more easily, reproduce more quickly, and depend less on large sources of life. In a world short of food, a small body can sometimes be a quiet advantage. Some species survived because they were flexible. They did not eat only one kind of food. They could change their diet, use seeds, insects, organic remains, roots, leaves, small organisms, or whatever sources of life still remained. When ecosystems are overturned, being too selective can become dangerous. Flexibility becomes a doorway. Some species survived because they knew how to shelter. Underground burrows, freshwater environments, mud cracks in stone, deeper sea floors, or environments less directly affected could become places of waiting. No refuge is absolutely safe, but sometimes reducing even part of the pressure is enough for a lineage to pass through the worst period. Some species survived because they were widely distributed. If a species lives only in a very narrow region, a disturbance in that place can erase all its chances. But if a group of organisms lives across many places in many different environments, the chance that some populations will remain becomes higher. On a changing planet-wide distribution is sometimes a kind of natural insurance. Some species survive because of luck. This may sound simple, but in the history of life, luck is always present. A population happens to be in the right place. A body of water does not lose oxygen as severely as another. A shelter still contains enough food. A lineage happens to possess traits that fit the new world by accident. Not everything is a perfect plan of evolution. Often, life continues because one small branch happens to stand in a place that is less damaged than others. But after surviving, life must do something even harder, diversify again. When ecological space is open, the remaining groups begin to branch out. One lineage can divide into many different ways of life. An omnivorous group can give rise to branches specialized in eating plants, eating meat, eating insects, living in trees, living underground, or living near water. A group that was once small can increase in size when large competitors are gone. A group that once lived on the edge of an ecosystem can move toward the center. Across millions of years, those small changes add up to a new world. This is why each great mass extinction is both a wound and a turning point. It erases many lineages, but it also changes old limits. It removes those that once ruled, but it also allows quiet groups to step into the light. It makes Earth poorer for a time, but from that poverty, new forms of life appear again. Even so, we should not understand this too lightly. A mass extinction is not good simply because new life comes afterward. The species that were lost do not return. Ancient reefs, trilobites, ammonites, non-avian dinosaurs, living communities that had existed for millions of years, all left the story of the planet. Life continued, but not without a price. After each recovery, Earth was still alive, but it was a different Earth. That is a very deep truth of natural history. When we see a bird flying across the sky today, we are not only seeing a small creature of the present, we are seeing a dinosaur branch that survived the end of the Cretaceous. When we see a mammal in the forest, we are seeing the descendants of mammalian lineages that once passed through a post-asteroid world. When we see flowering plants, insects, the sea, and modern coral reefs, we are seeing new chapters written upon the foundations of chapters that have closed. Every living creature today carries within it a long history of survival, not necessarily direct survival through all 5 mass extinctions in the same form. Not like that. But their lineages, their very distant ancestors, pass through the great boundaries of time. Inside the body of every modern species is the result of countless episodes of selection, countless adaptations, countless moments when other branches disappeared and one small branch continued onward. Perhaps that is why the world around us becomes different when we know this story. A leaf is not only a leaf, it is the result of a plant history that once changed the atmosphere, the soil, and the sea. A fish is not only a fish, it is an echo of ancient oceans, where life once passed through oxygen loss, sea level change, and long recoveries. A bird is not only a morning song, it is the living remainder of a dynasty that once seemed to have closed beneath the Cretaceous sky. Even we ourselves belong to that story. Human beings appeared very late in Earth's history. If the whole history of life were one long night, we would enter only near the end. But our presence depends on everything that happened before. If the crisis at the end of the Triassic had not opened the way for dinosaurs, the Mesozoic world might have been different. If the asteroid at the end of the Cretaceous had not changed Earth, mammals may not have had the same opportunity to expand. If earlier extinctions had not rearranged the oceans, the land, and the ecosystems, the history of life may have followed completely different paths. We do not stand outside that history. We are a small branch growing from it. And when we understand that the question, how did life rebuild Earth, is no longer a distant question meant only for fossils, it becomes a question about the very existence of the world today. Life rebuilt Earth by hiding when it needed to, by changing when it could, by spreading when opportunity opened, by turning empty spaces into beginnings, by not returning exactly as it was but becoming something new. Imagine the history of Earth as a forest after many seasons of storms. Some ancient trees fall and never stand again. Empty patches of ground open beneath the light. At first, the place may seem sad and bare, but then small shoots begin to rise. Grass covers the soil. Young trees stretch upward. Insects return. Birds arrive. New roots take hold in old earth. After many years, the forest becomes green again, but it is no longer the old forest. It carries the memory of what was lost, but also the shape of what has been newly born. Earth is the same. After every extinction, the planet does not erase its memory. It keeps memory in stone, in fossils, in the thin boundaries between ages, in the chemical composition of sediment, in the living groups that remain today. All of them are traces of a past that has changed direction many times, and life somehow still learned how to go on. Not because it is invincible. Life is deeply vulnerable. A species can disappear. An ecosystem can collapse. An ocean can lose oxygen. A sky can darken. But life on a large scale has a strange resilience. It does not lie in any single species, but in diversity, in many different ways of living, in evolution's constant capacity to experiment. Diversity is part of that strength. When the world changes, no one can know in advance which trait will become an advantage. In peaceful times, a highly specialized species can be very successful. But in crisis, that specialization can make it fragile. A less conspicuous species, one that lives more widely, eats more flexibly, reproduces more quickly, can become the one that continues. Because life has so many forms, so many strategies, so many ways of existing, when one road closes, sometimes another small road remains open. That is why every living creature, no matter how small, can carry a profound role in the larger story. An insect species, a small fish, a riverside plant, a burrowing mammal, a forest bird, all are threads in the broad fabric of life. If too many threads are pulled out, the fabric weakens. But the richness of the threads is also what gives the fabric a chance not to tear completely. When we look back at the 5 great mass extinctions, we see a rhythm that repeats, yet is never exactly the same. First, there is a living world. Then the environment changes. Ecosystems are tested. Many species disappear. Some species remain. Empty spaces open. Life reorganizes, and a new world begins. That rhythm is not gentle. It is full of loss. But it is also why Earth's history has so many chapters. If everything were unchanging, life may have remained in a very different form. If every crisis erased everything, the story would have ended long ago. But reality lies between those two things. Earth changes violently, and life is flexible enough not to be extinguished completely. This final chapter, then, is not only an explanation, it is a looking back. From the Ordovician seas retreating beneath a cold sky, to the Devonian reefs suffocating in oxygen-poor waters. From late Permian Pangea, hot, dry, and unstable, to the Triassic, where an old world closed so dinosaurs could expand. From the Cretaceous sky ignited by an asteroid, to small creatures living through the darkness and opening the way for a new world. All of it leads to one truth. Life does not survive by remaining unchanged. It survives by changing. And perhaps that is the most beautiful thing in this long story. Not everything lasts forever. Not every species is saved. Not every world returns. But from what remains, life always finds a way to continue weaving the story. It takes the broken pieces of the old world and uses them as the foundation for the new one. It crosses geological boundaries through small bodies, humble abilities, and quiet strategies, whose true meaning sometimes becomes clear only millions of years later. If you listen closely enough, perhaps that entire history is still softly echoing around us, in the sound of leaves at night, in the insects outside the window, in distant birdsong in the morning, in the breathing of the forest, in the waves moving toward the shore, then drawing back again. All of them are descendants of worlds that were once tested. All of them are proof that life, though fragile, has passed through the narrowest doors of time. And as we stand in this present, looking back into that deep past, we do not see only 5 extinctions. We see 5 times Earth changed its face, 5 times life lost so much, and 5 times from quiet survivors, this planet began to be rebuilt. Not by miracle, but by time, by adaptation, by diversity, by very small beginnings. After the extinctions, Earth did not return to what it had been, but it remained alive. And from that survival, eventually there came forests, blue seas, birds in the sky, small mammals, human beings, and us. Tonight, sitting quietly in a very brief moment of the universe, listening to the long story of a planet that has nearly changed everything many times, but has never stopped writing the history of life. And here our journey tonight through the 5 great mass extinctions of Earth slowly comes to an end. From the ancient Ordovician oceans, where life once spread across the shallow seas, we have passed through icy upheavals that changed the entire planet. We entered the Devonian when the first forests rose upon the land and quietly transformed the seas. Then we stood before the Permian, one of the harshest trials life had ever faced, when climate, ocean, and land all fell into a vast crisis together. After that, we moved through the Triassic, where an old world closed and the door opened for the age of dinosaurs. And finally, we looked up at the sky at the end of the Cretaceous, where an event from space forever changed the fate of the non-avian dinosaurs. And from that empty space, smaller creatures, began to step into a new chapter of Earth. Perhaps what makes this story so haunting is not only the scale of those events, but the quiet endurance of life. It does not always survive by strength. Sometimes it survives by hiding, by becoming smaller, by waiting, by adapting, and then slowly rebuilding the world. If you are still listening in these final minutes, thank you for joining me on this very long journey through deep time. Please subscribe to the channel and follow the fan page so we can continue these storytelling journeys before sleep together. And if you would like, leave a comment and let me know, in the next episode, would you like to hear about the sixth extinction? The world of dinosaurs, or the strangest ancient creatures that ever lived on Earth?